It's time for galaxies. Galaxies are, well, a big collection of stars, but that's not it. That's not the entire definition. It's stars and gas and dust all being carried by the same gravitational field. So they're all tied together by gravity. So galaxies, stars, gas, and dust, all flowing through the universe in a group held together by the same gravitational field. Usually that gravitational field is created by a supermassive black hole at the core of the galaxy. According to Hubble, galaxies are everywhere. If you look up in the sky in any direction, the tiniest little speck of the sky will have thousands of galaxies in it if you can get a telescope to focus on that tiny little spot. Hubble's law. Hubble said, if you take this number and you set it equal to the velocity divided by the distance, that's going to give you the same number for every galaxy. Every galaxy's velocity divided by its distance from our galaxy is going to give you a constant number. And that's Hubble's constant. It's 75 kilometers per second per megaparsec. Megaparsec is a distance. It's a distance. Like there's a whole entire PowerPoint just on that. I'll do that later. So Hubble's constant and Hubble's law very simple. H equals v over d. If you know the velocity and you know that 75 is Hubble's number, you can get the distance. You just take the solve for d. Basically, you just switch the d and the h, and you get v divided by 75. That's the distance in megaparsecs to the galaxy that you had the velocity with. If you have the distance and you want the velocity, you just have to multiply the distance by 75, and that's how fast in kilometers per second that galaxy is going based on its distance. So pretty simple stuff. Hubble didn't just discover that there were more than one galaxy. Hubble didn't just discover that the universe is expanding and that the galaxies are moving away from each other. He didn't discover redshift at all. He used redshift, which was Doppler's idea, Doppler effect, and Doppler, the scientist, came up with the idea of redshift for galaxies, for stars, really. And but Hubble didn't discover Doppler effect. Doppler did. Hubble used Doppler effect to discover redshift of galaxies. So Hubble defined the types of galaxies for us. He gave us the names of it: elliptical, spiral, and irregular galaxies. And there's two types of spiral ones. So elliptical galaxies are ellipse-shaped. They are football or sphere-shaped, anything from football-shaped to sphere-shaped. They are almost all older stars and very, very little loose gas and dust. Very few nebulas. That's elliptical galaxies, probably very old. Hubble said they were the youngest. He had it backwards. He said spirals are the oldest and elliptical are the youngest, but it's not true. As the galaxy rotates over many, many billions of years, those spirals start to blend together and you get an elliptical shape. He said there's spirals with 3 to 7 or 8, well, 3 to 6 is common, 4 to 5 is normal. Spiral arms coming out from a large, very bright center, and that's a spiral galaxy. They have medium-aged stars and a medium amount of gas and dust, so they can still make new stars. Barred spiral, it has a bar across the middle. There's the core, there's a bar coming out on each side, and one spiral arm off the ends, both ends of the bar, so 2 total spiral arms. Barred spiral. The spirals and barred spirals about the same age, about middle-aged, and medium amounts of gas and dust, so they can still make new stars. And so the stars range in age from new to old. And then irregular galaxies, lots of gas and dust, lots of new material to make new stars out of, lots of nebulas. That's the gas and dust. And so irregular galaxies, unless it's the result of a collision, an irregular galaxy is going to be younger. The large and small Magellanic Clouds that are in orbit around the Milky Way are very young stars, lots of gas and dust, lots of new stars being made. Large and small Magellanic Clouds are orbiting the Milky Way galaxy. But then the Milky Way and Andromeda are spiral galaxies. Andromeda is the one that's headed right for us. It's going to collide with our galaxy someday, 500 billion years from now. No, sorry, let me say this right. Half a billion years, 500 million years from now. So different types of galaxies. Hubble said the spirals are old, and as you get closer to elliptical, they become younger and younger. So you go elliptical to spiral in age, and irregular is the oldest because they're just falling apart. But he was wrong. Hubble did it backwards. It's irregulars are young, then they start to rotate and become spiraled. Then those spirals start to blend together and they become elliptical. That's the correct way to go. Irregular through elliptical. Irregular young, elliptical old. That's how it works. And we know this because of the age of the stars. There are more red and orange stars in elliptical galaxies, and there are more blue and white stars in irregular galaxies, and then spiral galaxies have kind of a mix of both. And so we know that's the ages of the galaxies based on the ages of their stars. Let's see here. Hubble has designations for galaxies. Is the spherical ellipses are E0s, and then as it gets more and more longer, elongated, I guess, if it gets more elongated, it goes E3, E5, E7, and then if it's almost got spirals but not quite, it's elliptical but almost has spirals, it's an S0. And then the spirals, there are SA, SB, and SC. SA has 2 spiral arms, SB has 4 spiral arms, SC has multiple spiral arms. But then there's barred spiral, SBA, 2 close-in spiral arms, SBB, 2 slightly farther out spiral arms, and SBC, 2 spiral arms that are kind of extended out away from the center of the galaxy, not near the center of the galaxy. And so you've got all these designations. I'm going to show you a bunch of pictures of galaxies and ask you, what does it look like, an elliptical, a spiral, or an irregular? Galaxies collide. But the weird thing is, when a galaxy collides with another galaxy, I'll put some pictures of colliding galaxies up here too. When a galaxy collides with other galaxies, stars are ripped out of one galaxy and pulled into another galaxy. Stars are ripped out of the other galaxy, pulled into the first galaxy. Stars are ripped out of the galaxy and accidentally just drift off. So you get all kinds of situations happening. But the solar systems for those stars, the planets around those stars, never feel the effects of the collision. Between all the stars, there's this star over here and this star over here, it's light years between them. You can have 5 or 10 stars go in between the normal 2 stars, and they don't ever notice, because stars are really, really far apart. The secret to understanding outer space is there's a lot of space in space with just nothing in it. So when a star zips between the 2 other stars, it could be 2 light years away from both of them. It could be 10 light years away from both of them. They won't have any effect on the solar system that it's going past, unless it literally collides with another star. That almost never happens. So colliding galaxies, there are not stars colliding with each other all over the place. That's not how it works. Most of the stars just pass through each other. And some of the stars from one galaxy will be orbiting the black hole of the other galaxy, and some of the stars from the other galaxy will be orbiting the black hole of the first galaxy. And some just get scattered and become rogue stars, rogue solar systems. It does happen that way. But for the most part, everything is just kind of continue on the way it was. That's just how colliding galaxies work. I'll show you pictures of what I mean anyway in a while. Our galaxy is the Milky Way, and Mr. Gilner's favorite candy bar is the Milky Way. So the Milky Way galaxy is where we are, because if you look up in the sky, people said, well, that looks like spilled milk. It looks like a Milky Way, a pathway made of milk. And that's where it got its name. We are in a spiral galaxy. The Milky Way is a spiral galaxy. We can't see the spirals because we're in this galaxy. We can't see what our galaxy looks like until we get a probe out of the galaxy, and we've barely gotten probes out of the solar system. I mean, we've barely gotten Voyager 1 and Voyager 2 anywhere near the edge of the solar system yet. And some people say, well, that's not even the edge of the solar system. That's just the heliopause. That doesn't count. We'll go into heliopause and heliosphere later. It's got nothing. It's the outside edge of the solar system, but it's still part of the solar system. So the Milky Way galaxy, 100,000 light years across in diameter. So for light to go from one side to the next it takes 100,000 years at light speed for light to go from one side of the galaxy to the other. 12,000 light years from top to bottom. That's 12,000 years for light to go from from the top to the bottom. Well over 1 billion stars. It could be a lot more than that. We can't get out of this galaxy to turn around and look back at the galaxy to even tell how many stars are really in our galaxy. About 13.2 billion years of age. That's because they've estimated the age of the stars in the galaxy and the supermassive black hole at the center of the galaxy, and had to figure out how much stuff it had to absorb in its time to grow to that size, and figured, about 13.2 billion years old. And it has 4 to 5 spiral arms. We can't tell if it's 4, we can't tell if it's 5, we don't know. So how do we know we're in a spiral galaxy? And how do we know it has 4 or 5 arms? If you look that way in outer space, you notice a lot of very close stars and a lot of very far stars and a lot of stars at a medium distance. But if you look that way, out of the galaxy, all of the stars are a large distance away. So we're in a spiral arm, and if we look down along the spiral arm, we see stars everywhere, far away, close up, all kinds of stars. If we look back that way, far away, close up, that's along the spiral arm. But if we look, and we're on the edge of the spiral arm, if we look that way, we see a lot of empty space and then a bunch of stars. And if we look that way, just a bunch of stars. This is the whole galaxy, the whole core of the galaxy. If you look over there, the Milky Way, when you look up in the sky and you see that line of stars that looks like spilled milk, that's the core of the galaxy. That's Sagittarius. And at the center of Sagittarius is the Milky Way's Sagittarius A star supermassive black hole. That is looking at the core of our galaxy, right up that direction. And we look the other direction, away from the core of the galaxy, is just empty space. So we're on the edge of a spiral arm. Not forever, because the stars don't stay in the same positions in the galaxy all the time. The spiral arms are stars close together due to a gravity wave. Hold on. Gravity wave brings the stars close together, and then that gravity wave goes past and the stars spread out a bit. And then the gravity wave moves on to another group of stars, and the stars are spread out really far, and we're between gravity waves, so we're between spiral arms. Well, we're just on the edge of one of those spiral arms. But I don't know, are we headed into the gravity wave to become closer to the other stars, or are we headed out of the gravity wave to become really, really far from all the other stars? I don't know. We'll have to wait a few billion years, maybe 1 billion years, to find out for sure if we're staying in this spiral arm or moving out of it. We'll see. So we are in a spiral arm. We can tell from the concentration of how many stars are in each direction. And if you look up and down, you see to the top of the galaxy, there's close stars and far stars, but not as many as if you look that way. And if you look south or down, there's close stars, there's far stars, but not as many as if you look that way, or that way, or that way. But if you look that way, there's no stars close by over there. The nearest stars are the next arm over, and that's spiral arm, pretty far away. So that's the Milky Way galaxy. I think we're good to go on this video. So that's galaxies. I will show you as many cool images as I can of galaxies, and we'll practice classifying them. I'll show you different types, and I'll ask you, is it spiral, is it elliptical, is it irregular, and so forth, in a bit when we do the assignment. So that it's pretty interesting stuff. The fact that there are trillions and trillions of galaxies everywhere, every direction you look, and if you just focus on the tiniest speck of space, there's a bunch of images called the Hubble Deep Field images. They focus on a tiny speck in space for a month, and they get these images of thousands of galaxies in one image, and they're all over every single direction. Doesn't matter which direction they point Hubble telescope, they're all over the place. Trillions of galaxies with trillions of stars each. That's a lot of stars. That's a lot of planets around those stars. Almost every star we've found has planets passing in front of it. We can see the shadows of the planets as they go by. There's planets everywhere. There's hundreds of quadrillions of planets out there. Life? I don't know. Intelligent life? I can't find it on this planet, so I don't know. We'll see. But that'll be my time for now. I got about 5 seconds left.